In modern artificial intelligence, there is a core assumption that drives the entire field. To truly understand language, a machine must be trained on it. This training relies on a massive, continuous cycle of trial and error. Algorithms use gradient descent to iterate through billions of words over multiple epochs, slowly adjusting their internal parameters to better predict how words relate to one another. Maintaining this process requires a heavy physical and financial investment. It demands specialized warehouses packed with thousands of high-end GPUs and enough electricity to power a small city for the duration of the training run. These costs have effectively created a moat around the industry. Because of the hardware requirements, the development of foundational AI models is currently restricted to a few ultra-wealthy organizations. As a result, the current AI economy is largely valued on the belief that raw computational brawn, having more chips and more power than the competition, is the only viable path to artificial intelligence. But researcher Daniel Gray is testing a different hypothesis. He claims that the semantic meaning within a corpus can be computed directly, using formulas that don't require a neural network at all. While the industry standard relies on massive GPU clusters, Gray's approach, called Res2vec, is designed to run on a standard CPU, the kind found in a typical laptop. If this method can match the results of traditional models, it would suggest that we have spent billions of dollars treating a solvable mathematical problem as a brute force search operation. Both traditional machine learning and Res2vec begin at the same starting line, a co-occurrence matrix. This is essentially a giant grid that tracks how often specific words appear near each other across a billion tokens. In a traditional pipeline, this matrix enters the learning phase, where models spend weeks guessing at underlying patterns through iterative optimization. Res2vec takes a different path. It abandons iterative guessing entirely, instead using classical linear algebra to derive the relationships between words. First, pointwise mutual information strips away noise, isolating significant associations. Then, singular value decomposition compresses that massive matrix into a dense vector space, preserving its structure. SVD provides a deterministic output in a single pass. No training, no guessing, no epochs. When you use a deterministic formula, you arrive at the answer directly. This highlights a potential inefficiency in the industry, training a model for weeks to approximate a result that can be calculated in hours. Usually, determining the dimension of an AI model, how many data points define each word, requires what's called hyperparameter tuning. You try 50, try 100, try 300, guessing what works best. Res2vec calculates the optimal dimension using resonance theory, but the math is recursive. You need the resonance to find the dimension, and the dimension to find the resonance. Yet, across a billion tokens, this recursion hits a stable fixed point, settling exactly on 188 dimensions. The fact that this calculation consistently resolves to a specific, self-consistent number suggests that the relationships in human language may have an inherent geometric structure, one that can be derived through calculation. The results of this approach are concrete. Gray's first implementation of the model processed a billion tokens in just 174 minutes, using only standard CPUs. Compared to Res2vec on equivalent hardware, that is a 59-fold increase in speed. More significantly, it represents a drop to just 1.7% of the traditional computational cost. It is important to note that this is an unoptimized proof of concept. Currently, Res2vec achieves about 80% of the accuracy of traditional, highly tuned models on human similarity benchmarks. But that performance gap isn't necessarily a failure of the math. It demonstrates that semantic derivation is functional and repeatable. It is now a matter of refining the formula rather than just adding more hardware. If the 20% performance gap can be closed through better math, the barrier to entry for building these models shifts. The reliance on massive GPU infrastructure may eventually be seen as a temporary workaround for a problem we didn't yet understand. This creates a direct challenge to the valuations of companies that have built their entire competitive advantage on the scale of their hardware. The AI industry is currently optimized for a world where only the biggest clusters can produce results. But these findings suggest that the era of brute force optimization could be highly sensitive to the arrival of more efficient mathematical derivation.